Right, let's head into some really interesting stuff. The fundamental counting principle. So let's get ready. So unpack some t-shirts and go into it. And, let's make it mass for good old times with the old music too. Okay, so the idea here with the fundamental counting principle is that we're going to look at permutations. So permutations are arrangement of items, and the positional order of the items is important. So what we're looking at is maybe something like 2, 3 is quite different to 3, 2. It's not like we're just picking the number 2 and the number 3, or picking the number 3 and 2. That order, 2, 3 or 3, 2, is going to be important. So we've got 2 bits here. We're only going to look at this next part tomorrow or the next one. But in this one, we're going to look at, we've got successive choices. So we're going to choose some things and we're going to multiply. And we're going to look at that right now to make sense of what that means by multiplying. So let's do it with an example. You can see I've got my shirts and pants ready to go here. I know, the excitement. So in our shirts and pants example, my example is that I've got 2 different types of pants, 2 pant, and I've got 3 different types of shirt. And the question is, how many different combos can I have? So how many different outfits? I guess outfits, not combos, eh? Would that be better? So how many different misfits, so how many outfits could I have with 2 different types of pants? I've got the blues and the browns here, and 3 different shirts, green, purple or black. And don't get all fashion conscious here. Anything can go together in this one. Let me move there. You can see all the, I always forget which side, all the pants and shirts. So how many different outfits can we have? Okay, so you may do this in different ways. I've purposely got the pictures so that we can go, well, for the blue pants, we could wear the blue pants with any of these shirts. There we go. This is working quite well, I think. Or we could have worn the brown pants with any of the different shirts. So I'm going to put my shirt on first this time and say pant, 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 and just, I really put the head in there. I wish I could have that in front. I'm sure there's a way. Let's see. Well, that's the best, the best I could do. Anyway, so you got your combinations, I got my combinations, and I guess one way to think about this is to say, well, let's look at the pants there, 2 different pants, and with each of those pants, we could have had 3 different shirts. So we saw there were 2 pants, here the 2, and with each of those, we could kind of make lots of 3, so we had 2 times 3. That's if we put our pants on first and then our shirt. But it wouldn't really matter if we looked at it the other way around and said, well, there were 3 shirts, and with each shirt, we could have paired it with 2 pants. So it doesn't really matter. Whichever you go for, you got a cool outfit and you got 6. So that's kind of that idea of multiplying. So if we added into the mix, some shoes, and you had different shoes and you had different socks, then you just keep multiplying by all the things. Okay, enough of that. Let's head into examples so we can make sense of it. So standard number plates have got this format: 3 alphabetic characters, excluding Q and the vowels A, E, I, O, U. Why do you think they exclude those letters? I guess, man, I don't know. I haven't read up about this. So let's see what you have to say there. Instead of me hazarding my guess, let's have a read what you say and we'll bring that into the next one. So we've got how many different standard plates are possible if repeating digits are allowed. So what I kind of like to think about this is standard, we've got 3 of those and then 3 of those. So 3 alphabet characters. So 1, 2, 3 of those. And then we've got 3 numeric digits. 1, 2, 3. So there's kind of what we need to form. For our alphabet characters, we're allowed to repeat them. So we can have, there are 26 letters in the English alphabet, I believe. So 26, and then we minus 1, 2, 3, 4, 5, 6, right? So minus 6 gives us 20. So in other words, we could have chosen 20 over here. We could have chosen 20 different ones over there. So this is where our multiplication is going to come in. And then we've got 3 numeric digits. Now for the numeric digits, we've got 0 up to 9. So if you count that up on your fingers, there are 10 of those. So we've got 10 different options there, 10 different options, 10 different options. So expanding on that idea of the shirts and the pant, we've got over here, we could go 20 times 20 times 20, and then keep multiplying by 10 times 10 times 10. And if you wanted to kind of write that a little bit quicker, you could have had 20 to the power of 3 times 10 to the power of 3. Doesn't really matter. They both showed quite nicely. And that equals, into the calculator goes. Oh, I didn't do it in the calculator yet. So go for it, and what do you get? Okay, well, you got that. I've lost my calculator in my way. But there we go. Calculator. Ah, there it is. See, it was missing the little jingles. So we go 20 times 20 times 20. I feel like here's easier to do that. 10, there's even a Q button. So 8, 1, 2, 3, 4, 5, 6. This is going to be finance mathematics all over again, right? Missing out all the digits. So I think there's 6 there, but, double check that. Okay, so a pack of cards without without jokers. Yeah, good one, eh? So, where are we? Okay, one more week. So a pack of cards without any of me contains 52 cards. If you choose 3 cards successively without replacing them, hopefully successfully too, what is the number of possible outcomes? So again, let's just think of this idea that you're taking the first card, then the second card, and then the third card. There are 52, so there are 52 options when you take your first card. But in the second one, you've taken one and you're not returning it. So there are only 51, and then there are 50 over there. So therefore, our calculation is number of possible outcomes, 52 times 51 times 50. And what do you get? Okay, well, I think I need my calculator again. And let's get it up here. Well, it's up on my screen. There we go. And we've got, where is it? 50 times 52 times 51 times 50 gives us 132,600. 132,600. Okay, cool. That's onwards, upwards. That is the number place. So that. Okay. Next one is the digits. I'm actually going to hit a quick pause because we missed 1 or 2 from the workbook. So I'll be back. Boof, what a jump cut we are. Okay, so there we are. Bob has 6 pairs of trousers, 8 long sleeve shirts, and 10 ties. How many different outfits are possible? So given that we did one very similarly earlier, kind of maybe just jot down quickly what's your method, and then what answer do you get? Okay, so again, I'm going to kind of look at it here. We've got 6 pairs of trousers. So kind of first, when we look at the trousers, there are 6 different options. There are 8 long sleeve shirts. So if we're looking at long sleeve shirts, I know you didn't, I was going to say you thought I wasn't an artist, but you've seen my minibuses and that before and that. So 8 of those and 10 ties. So let's do our ties over here. So in our last option, we're going to choose, what does a tie look like? Something like that. Could practice these things. So there we go. We've got that. So the number of outfits that are possible, we've got, the number, I guess, of outfits is 6 times 8 times 10. 6 times 8, 48 times 10, 480. That is quicker than the calculator. Okay, so there we go. That's how we do that with Bob and his outfits. Okay, a computer login password has to be 5 characters long. So I kind of already got this idea of 1, 2, 3, 4, 5. Not going to be too strong, this password, is it? So can be any combination of 26 letters of the alphabet and 10 numerical digits, 0 to 9. So there are not that many options here, really. So just at a guess, without working it out, how many different codes do you think are possible? Okay, so you've got some sort of guess. Maybe they're 100, 1,000, 100,000. I don't know. Let's have a look. So we got our 26 letters plus our 10 numericals. We got 36 different options for each of these. So 36, 36, all of those. So we just need to multiply these together. So in other words, that's 36 to the 5. And that's going to give us, let's see, come on, calculator, where are you? Hello? There we go. Okay, so 36 to the power of 5, that's equals, maybe I should have just done this originally, huh? Save myself the trouble of getting that wrong. There we go, that number, 6 million, is it? I don't know. Whatever long number that is, there are a lot of different possible codes. Now, just as a quick aside, because I think it is worthwhile maybe just thinking about this. There isn't a question like this here, but let's say that the code was only had to be 1 digit long. Then we would have had 36 options. 2 digits long, and we would have had 36 times 36 gives us 36 squared, which is 36 squared gives us that thing over there. So that's if we had 2 digits. And if we had 3 digits, then we would have 36 times 36 times 36, 36 cubed. So if we just times that by 36, each time we do this, there are 36 times as many options. So it's growing, or times another 36. So if we have 4 different digits, that would be 36 to the 4, which, can you see that this, every time you add another option, so let's just check that my numbers were right here. Did I times that by 36 or just by 3? Let's see, 36 times 36 is 1296 times 36. No, the second number was wrong. It should actually be bigger than that. So every time that we add another digit, we timesing that previous number by 36. So the point that I want to drive home here, because it is such a good security one, is when you're doing a password, the difference between going, oh, well, I changed one of the 3 or one of the E's to a 3 or an O to a 0, all you're going to do is confuse yourself and your password is not that much stronger. Have your special characters along the way, whatever they are. And yes, you might have some numbers. But if you want to have a really strong password, just make it really long. So give yourself a story like maths is really fun. If that's your password, it's going to be really hard to crack because it's so many characters long. So there's so many options. Okay, that is my quick aside over my comp sci background. Okay, so let's go back in and have some last 2 questions. And that is, well, those are, consider a 4-digit code. So I'm already just going to go 4 digits. So it's got 1, 2, 3, 4. 4, a wonky 4th digit there. And, a little pause, just read through the question to make sense of it by yourself first. Okay. Now we can use any of these digits. And let's see what happens in these 2 cases. First case is that we're not allowed to repeat. So in this case, for our first digit, we could have any one of those 10 digits as the first digit. Cool, so there are 10 options. Then for our second digit, well, there are only 9 options now. Because if we chose the number 0, we could choose one of those 9. If we chose the number 1, we'd still have 9 options for our second digit. So hopefully that kind of works. Okay, and then for our third digit, we only have 8 digits to choose from. And for our fourth, we only have 7 digits to choose from. So therefore, for our possible outcomes, we're going to multiply those all together, and I get 5040. Right, 72. Let's just do that on the calculator quickly to check. Times 8 times 7, not another times, 504. Okay, so that's if we cannot repeat, but if we are allowed to repeat digits, then it changes a bit because we can choose 10 for the first one. And in fact, we can choose any one of those 10 for the second, any one of those 10, and any one of those 10 for the third. So in that case, we're going to have 10 to the power of 4, which is 1 and then 4 zeros. I'm just going to check that on my calculator. 10 to the 4, I'm not loading it up. 1, 2, 3, 4. Just to make sense there. Just to make sense. Double check. Okay, so that's our idea now if we can repeat or not. So let's take that into a slightly juicier example. 4-digit number are forward. So 1, first digit, second digit, third digit, fourth digit. Again, a quick pause just so that you can read through it before I read through it. Okay, so we got these. We can use 7 digits now. 7, 6, 5, 4, 3, 2, 1. That made life a little bit better and easier. Okay, so I'm not going to put anything in here because let's see what each of these questions asks. How many different 4-digit numbers could be made? Well, if they're different 4-digit numbers, then how many different ones could we make? Well, I don't know. Let's see what you have to say for that one. And let's see what I get in that one. So we got how many different. Now, remember that no digit can be used more than once. So we can use any of the 7 for the first one. But then for the second digit, we can only choose from 6 because we've used one of them up already. 5 for the third one and 4 for the fourth one. So therefore, for part 1, we can just multiply those together and I get 840 when I do that. Okay, then let's head into question 2 and see. How many even 4-digit numbers could be made? So what you're thinking and kind of trying to solve this when we've got even, let's move on. What's your thinking for this when we try to look for even 4-digit numbers? What are we going to do here? Well, if it's even, it means that this last digit out of these has to be a 2, a 4, or a 6. So this number has to be 2, 4, or 6. It can't be a 1 because then it would be an odd number. 3, 5, or 7, those would be odd numbers. So looking at this block first, the last digit has to be one of 3. So when you've chosen one of those 3, then you've used up one of your digits. So for your next one, you can choose 6. And now it doesn't matter what order you go. So you could have gone 6 for that one, 5 for that one, 4 for that one. But you could have to choose one of 3 for that last digit there. Now, as I said, the order doesn't really matter because I kind of almost want to work backwards and go, well, you've chosen this one. Now you're going to choose 6 for that one, 5 or 4. Or maybe the real point is you must have done this one first. And then from there, you're going to fill in the rest from the remaining 6, 5, and 4 digits. And you're going to multiply those out and I get 360. Okay, let's kind of take that thinking forward into part 3 and say, okay, so how many of the 4-digit numbers would have a value greater than 6,000? So again, describe how is this going to help us solve this? What are we thinking? Well, if it's greater than 6,000, this has to be 6,000 because the smallest number we could have is 6,001. Now, given our digits, the smallest number we could actually have would be 6123, I guess. But the point is this needs to be a 6 or this has to be a 7. So there are only 2 options for that first one. So you're going to choose one of 2 numbers, either 6 or 7. And then when you choose your next number, well, there's 6 numbers left to choose from. Because you've either chosen 6, in which case you're going to choose 7, 5, 4, 3, 2, 1. Or you've chosen the number 6 or the other one. I can't remember. But you're going to choose one of the other 6. And then they're going to be 5 to choose from and 4 to choose from there. So that's kind of our thinking with all of these. Start with the one that you have to make a decision on. So for this number 2, we started there because they had to be even. For this one, we're starting with the first digit because it has to be a 6 or a 7. Okay, and you multiply those things out. And, I'm not going to ask you to do it on the calculator. You get 240. Okay, so last question. And again, the question is going to be kind of what's your thinking going to be on this. And I'm going to redraw the blocks down here so I can see them. So how many of the 4-digit numbers would be even and would have a great number? Sorry, let's try that again. How many of the 4-digit numbers would be even and would have a value greater than 6,000. So kind of some sort of combination of 2 and 3. Just ideas and thoughts here. So we got one of two options here. So this end digit has to be even. So it has to be 2, 4, or 6. And this first number has to be 6 or 7. Now, if this is 6, our last option could only be 2 or 4. It can't be 6 anymore. So only going to be two options. If this is a 7, then this could be 2, 4, or 6. So there are two different things that we have to think about. So let's do it down here where we can see it here. We're going to have a bit of an OR going on. In our first cell, let's say that we put a 6 in this first block. Then the last option could only be a 2 or a 4. So there would be two options over there. And for our middle numbers, well, we've chosen two numbers, so there are only 5 left to choose that one and 4 left to choose that third digit. So let's just rewind on all of that, but let's actually rewind it and talk about it properly. So for our first digit, if it's the number 6, so I actually put the wrong number up here. If it's the number 6, there's only one way we can do that. Okay, so we've only got one option. If that's a 6, this last one could be a 2 or it could be a 4. So it's 2 or 4, which means that there are two different options for it. Which means we've chosen two of our digits. There are 5 digits left to choose for this one. And there are 4 digits left to choose for this one. So now we can multiply all of these together. Or, and remember, or means plus. So, and I say remember because that's what we did in probability before. Or our second option is that this first digit is a 7. And it has to be a 7, so there's only one option. The last digit could be a 2, a 4, or a 6. So there are 3 options. And then similarly, we've got 5 digits to choose from for the second one and 4 digits to choose for the third one. So if we combine these, so if we go that plus this, we've got 1 times 5 times 4 times 2, that's 40, plus there 1 times 5 times 4 times 3, that is 60, which gives us 100 different combinations. That was a nice one to end off with. Okay, well, that is that. Enjoy.
Make it best.